Hi everyone. Today I want to tell you a little bit about how to compute the area between two curves. This is material that we have already covered during the Zoom meeting for the most part. And towards the end of the video, I'll talk about the last part of section 6.1 that we didn't talk about in the meeting. But I want to go through the whole material again, just so you have that as a reference if you want to look at it again or see the examples again. Okay, so to start with, we're going to consider a picture like this, right? So we draw the x and y axis, and we have two different functions. Let's use different colors for them. So we have a function f of x. This is the graph y equals f of x. We have a different function g of x, y equals g of x. And we want to understand how to compute the area between these two graphs, right? Between these two curves. We're gonna set some bounds for these graphs. So let's say that we want to see the area between these 2 points. So let's say that this is A and this is B. Yeah, so we want to compute what is the area in between these two curves from A to B. So this whole area here. All right. So the idea, you can look on Stewart for a better picture than what I can draw here. But the idea is to chop up this area into very tiny rectangles and then sum all of them and send the width of the rectangle to 0 and get a good approximation of the area, right? As you send the width of the rectangle to 0, you get the exact area. It's a limit. But basically, you draw a very tiny rectangle like that, where the area here is delta x, and then you want to add the area of this rectangle, right? The area is base times height, right? So let's say that this is at a certain point, say x here, right? So the area of the rectangle is the base of the rectangle times the height of the rectangle, right? So the base is delta x, right? That's the length of the base. The length of the height you can compute by looking at this y-coordinate, which is f of x, right? If this is x here, this is f of x, and you subtract g of x. If you do that, you get this length here, which is the height. I'm going to write the height first. So f of x minus g of x. Oh, that looked ugly. F of x minus g of x is the height of the rectangle. You multiply by the length of the base. This is the area of this tiny rectangle. You sum all of them, right, from A to B, and then you take a limit as this delta x approaches 0, right? So this is what the area should be, and this limit is exactly the integral. Integral from A to B of f of x minus g of x dx, right? So this delta x turns into this dx here. This sum turns into this weird symbol. And you can think of this term here as the area of an infinitesimal rectangle. So a rectangle that's actually not a rectangle, it's just a line, right? It has 0 area, and the length of the base would be this dx, which is a strange number, like an infinitesimal number is what we call it. In any case, that's the formula for the area between these two curves, right? So the area is equal to the integral from a to b of f of x minus g of x dx. Okay. But one important thing for this formula is that this picture has to remain accurate. So there are some hypotheses that need to be satisfied. Of course, f of x and g of x need to be integrable functions. You need to integrate. But also, it's important that for x in the interval that we're considering, in the interval AB, this function f of x is bigger than or equal to the function g of x. Okay, this inequality here is saying that, you know, the graph of f of x is always above the graph of g of x, like in this picture here. F of x is purple, and it's always above the graph of g of x. This makes it so that f of x minus g of x is a positive number, which is the height of the rectangle, right? So if you, for example, in this equation here, you subtract g of x on both sides, you get the f of x minus g of x is greater or equal to 0, right? So this number here is positive, and it's the height of this rectangle. So if you don't pay attention to this inequality, you might, if you write this formula, you might get negative numbers here, and you're counting certain rectangles with negative area, and you don't want to do that. Right? So this hypothesis is important here. So this is the formula for the area as long as f is always above g. All right. So let's do an example, the example we saw in class. So example 1, let's compute an area using this formula. Compute the area between the curves y equals x squared and y equals 2x minus x squared. All right. So in these types of problems where you need to compute the area between the two curves, the first step is always to try to draw these curves. Okay, so we need to draw these two curves to see what the area between them looks like. And so, okay, so one of them is pretty easy to draw. X, y. Y equals x squared, that's just the parabola. Oof, that didn't look good at the end. Right, so this is y equals x squared. Now y equals 2x minus x squared. Drawing this is a little bit more complicated, but it's not so bad. So this is also a parabola, but because this the sign in front of the x squared term, right, the sign of the number multiplying the coefficient multiplying x squared is negative, this is a parabola, you know, as I said, the coefficient is negative. This is a negative parabola. It's sad, so it's gonna be a frowning parabola, like this. Yeah? And so we know that it's gonna kind of look like this. It's gonna curve down, but it's gonna be important for us to graph this appropriately to understand as well what are these x-intercepts of this parabola here, this negative parabola. Right? And to find the x-intercepts, you just need to set y equals 0. Right? So we set y equals 0. We see 0 equals 2x minus x squared. You can factor out an x here, x times 2 minus x. And you see that the x-intercepts are x equals 0 or x equals 2. All right, so it's right here, x equals 0. And then, let's see, I'm going to try to do this somewhat well, x equals 2. And so if you draw your parabola, it's going to kind of look like, oof, it's hard to draw. Yeah, like that, okay? So this is the graph of y equals 2x minus x squared. And the area between these two curves is this area right here. That's the area that we want to compute. Okay, so we can use our formula. The area is equal to, you see, you're going to integrate from, you look at the range of the x variable along your region. So you're going to start at x equals 0, and then you're going to keep adding rectangles until this area is finished here, right? So there's a certain point where the area finishes, and we don't know what point this is yet. I'm going to call it b, like I did before. So you integrate from 0 to b, yeah, you're going to integrate, and then it's going to be f, we're using this formula, f of x minus g of x, where f of x is the function on the top. Okay, so the graph on the top. In this picture here, the graph on the top is this purple graph. It's 2x minus x squared minus the formula for the graph in the bottom, which is just x squared dx, right? And so to compute this area, we first need to figure out what is this b value, right? Because once we figure it out, then we can solve this integral. Okay. So hopefully this is clear, and we talked about how, this sometimes part of the difficulty is also figuring out what is the region bounded between these two curves, right? Perhaps you would think, oh, I don't know, is it this region that's bounded between those two curves? So it's bounded by this graph, and it's also bounded by this graph. Why is it not this region? It's because this region here is bounded by this graph and this, but also the x-axis, and I didn't say the area between the curve y equals x squared, y equals 2x minus x squared, and the x-axis, in which case maybe this would be a good one. But yeah, sometimes it's hard. You draw a picture and you need to see what is the area that's bounded by these two curves. And if you just draw these two curves without the axes or anything, like this parabola and then this parabola, you see that the only area that is between that is that part, right? Which is what I drew here. That takes a little bit of getting used to, but maybe I'll leave that drawing there. I think it helps. I'll just put a little box around it. It's an explanation. Okay, not a box, but let's figure out b then. So to figure out b, what we have to do is, okay, how can we figure out this number? This number is the x-coordinate of this point right here, right? It turns out this is the x-coordinate of the point which is in the intersection of the two parabolas. And so you can use that information that this point is in the intersection to try to figure out what this number is, okay? So if you, for example, try to write the xy coordinate of this point, you know that the x coordinate is b, right? But now, what is the y coordinate of this point? And you can use the fact that this point lives in this parabola to figure that out. It's like, well, this point is in this black parabola. And on the black parabola, all of the points in this black parabola satisfy this equation, y equals x squared, right? So for all of the points in the black parabola, the y coordinate is equal to the square of the x coordinate. For our red point, the x coordinate is b, the y coordinate must be b squared, right? So why is the y coordinate b squared? Because it's on the black parabola, and on the black parabola, the y coordinate is always equal to the x coordinate squared, right? But you can also write a different formula for the x and y coordinates of this point. So the x coordinate is b, but you can also say that the y coordinate, because this red point is on the purple parabola, then it also has to satisfy this equation, right? All the points in the purple parabola satisfy that y is equal to 2x minus x squared. So the y coordinate is equal to 2 times the x coordinate minus the x coordinate squared. For our point, because this point is also in the purple parabola, the y coordinate must be equal to 2b minus b squared. So these are two different ways of writing the same point, right? But it has a certain x and y coordinate, right? It's not different. So this is equal to this. There are two ways of writing the same number, right? Which means that this number b needs to satisfy this equation. So figuring out what b is, you can say that it has to satisfy this equation. B squared is equal to 2b minus b squared, right? Because these are two ways of writing exactly the same y-coordinate of this red point, right? So if we solve this, we can figure out what b is. And so I'm going to send everything to the left here. This negative b goes to the left, turns into a 2b squared there. This 2b goes to the left, turns into a negative 2b. You can divide by 2 on both sides. You get b squared minus b is equal to 0. And then here you can factor out a b. b times b minus 1 is equal to 0. And if two numbers multiply to 0, it means that one of them must be 0, right? So either b is equal to 0 or b minus 1 is equal to 0, which means that b is equal to 0 or 1, right? B is equal to 0, or here b is equal to 1, right? So there are two solutions. What's going on? Well, the thing is, these two parabolas, they intersect at two different points, right? This red point and this purple point here, the origin, right? So this is this solution where b is equal to 0. It's talking about this solution. That's not the one that we're looking for. We want this point, right? This is when b is equal to 1. So for us, this one is not good. Right? So we find out that b equals to 1 is what we're looking for. All right, and now that we found b, we can compute the area, finally. So the area is equal to the integral from 0 to 1 now. We know what b is, yeah, of 2x minus x squared minus x squared dx, right? And now it's just solving an integral. It's a pretty easy integral to solve, right? So for this type of problem, the setup is really the hard part. Integrate from 0 to 1. Negative x squared with negative x squared turns into a negative 2x squared. And that's a plus 2x dx. We use fundamental theorem of calculus. Just compute the antiderivatives here. It's going to be negative 2. This you add power rule for the antiderivative. You add 1 to the exponent and then divide by 3. Plus, here you add 1 to the exponent, it turns into an x squared, and you divide by 2, it will cancel out that 2, right? 2x is the derivative of x squared. Right? You plug in your bounds, x equals 1 and x equals 0. So if you do that, you're going to get, plugging in x equals 1, minus 2 times 1 squared over 3 plus, oops, wow, I made exactly the same mistake in class. 1 cubed over 3 plus 1 squared minus, and you plug in 0 there, you get negative 2 times 0 cubed over 3 plus 0 squared. Now this is 0, like 0 plus 2 times 0 is 0. This is just 0, it goes away. And here you get 1 minus 2/3, that's 1/3, right? So the area is 1/3. 1/3 units of area, right? We're not talking about what are the units that we're using for this problem, but whatever it is, it has to be 1/3, right? So if the units that you're using for measuring the lengths in the x and y axis are meters, then you would find 1/3 meters squared, right? If the units are inches, you would find 1/3 inches squared. But that's not very important, not for this class, at least right now. Okay, hopefully the process is clear. Let's talk about now what are things that can go wrong, right? So what happens is there are certain more complicated situations where the functions kind of intertwine each other, right? So the functions you see here throughout the whole region, purple was always on top in the region that we're looking for, right? But it could be the case that, they kind of intertwine, and there are certain parts where purple's on top and certain parts where purple's in the bottom. So what care should we take for that type of situation, right? So um, how to handle situations where the functions intertwine. So let me draw a picture so we're all on the same page about what I'm talking about. So consider something like this: x, y. And then you have a function on top, this. So say that this is y equals f of x. And then you have a function in the bottom. Let me use green. Okay, so say that this is y equals g of x. And then we want to find the area between x equals a and b. So let me draw, say that this is b, say that this is a, right? And we want to find the area from x equals a to x equals b between these two curves, right? So we want to find out how to compute this area. Yeah. So let me give a name. Maybe this is area 1, area 2, area 3. Right? So the area in this case is going to have to be broken up because we can't use our formula through all of a and b, because the function that is on top and the function that is in the bottom switches in the different parts of the region, right? So in the beginning, purple is on top and green in the bottom, but then after this point here, green is on top and purple is in the bottom, and then it switches again, right? So these points are actually going to be important, the points where this switching is happening. What color to use? I guess pink. Right, so these points where there's some switching going on, let me call this C. Let me call this D. Yeah. So we have to use different formulas between these points, right? So the area is going to be A1 plus A2 plus A3. And each of these things will have a formula in terms of an integral, right? So A1 is going to be an integral from A to C. And now we use our formula. So you're going to sum the areas of these rectangles, and the area of the rectangle is the value on top, the height of the rectangle. Value on top minus the value in the bottom. So f of x minus g of x. And then the base of the rectangle, dx, right? So you sum all these tiny areas from A to C. And this is because f was on top. But now for A2, we're going to integrate from C to D. Now the function on top is g. The function in the bottom is f, right? So the height of a certain rectangle in here is going to be g of x minus f of x. And the base is still dx. And then A3, the last one, maybe already here, plus integral from D to B. Yeah, here's A3, integral from D to B. And now f is on top again. So the height of the rectangle is f of x minus g of x. Right, so that's how we would compute area in a situation like this. Okay, so you just have to be careful to, when you apply our formula for area. Let me go up. I gave you this formula. Oh, the area between the two curves is integral of f of x minus g of x. the things, this has always to be the function on top, and this has to be the function in the bottom, right? So this inequality here is important. That I said for x in this interval, f was always on top, g was always in the bottom. Right? Forces this to be positive, as I said. Okay, so let's go through an example to see what happens when two curves intertwine and see how we would break up the integral like this. Okay, so in this example, we're going to consider two curves given by trigonometric functions. So find the area of the region bounded by the curves y equals sine of x, y equals cosine of x, x equals 0, and x equals pi over 2. Okay, so the first step again is to draw the region. In these problems, you really need to draw to understand what you have to do to compute the area. So I'm going to start by drawing the axes. Okay, x and y. And these curves, sine of x and cosine of x, are more complicated than these ones. So start with the easier ones. For example, x equals 0. This is the line of all points that have x coordinate equal to 0. These are all the points in the y-axis, right? So all the points in the y-axis have 0 x coordinate. So this is x equals 0 right here. And x equals pi over 2, let me draw it. Pi over 2 is right here. And if you want all the points that have x coordinate equal to pi over 2, you're going to get another vertical line right here. X equals pi over 2. So whatever region we're going to draw has to be between these two lines, right? So we know already that it's going to be bounded by these two lines. So we know that it has to be inside of this strip here. Now, in this strip, to draw sine of x and cosine of x, let me mark, they oscillate between 1 and negative 1, right? So let me move that equation down here. Maybe I'll put it here. So if this is y equals 1, right, let me also continue it all the way to the other side. Then to plot sine of x and cosine of x, you can, for example, think of the unit circle. Right, so for example, sine of x, when x is equal to 0, well, you can think of the angle 0, right? At angle 0, the x coordinate of the angle 0 will be cosine of 0, and the y coordinate will be sine of 0. And sine of 0 is the y coordinate of this point, which is 0, right? This point has 0 y coordinate. So sine of 0 is equal to 0. That's where sine starts. And sine of, once it goes all the way to pi over 2 here, sine of pi over 2, then you're going to look at this point right here on top, right? This is angle pi over 2, 90 degrees. The sine of pi over 2 is the y coordinate of this point, which is 1. Right? So sine of pi over 2 is 1, and the function sine just does that. Right? Now for cosine, it's pretty similar. Cosine of 0, well, you look, here's the point of with angle 0, right, in the unit circle. Cosine is the x-coordinate. The x-coordinate of this point is 1, right? So cosine of 0 is 1. That's where it starts. Cosine of pi over 2, you look over here at the point with angle pi over 2. Cosine is the x-coordinate of this point, which is 0. And this point has x-coordinate equal to 0. So you mark it there. Cosine starts there, and then it goes down there. right? So these are these two curves, right? So cosine I drew in blue, and sine I drew in purple. But we want the area between them bounded by these two vertical lines and these two curves. So we get this area here. Right? That's the area that we're trying to compute. And you see that in this example, there's a switch, right? So there's this part, area 1, and this part here, area 2. And on area 1, in this region 1 here, the blue is on top, so cosine is bigger than sine. But then on the second part, the area 2, sine is bigger than cosine. Right, so it switches. The area of the region that we're trying to compute is equal to A1 plus A2. And, well, we need to figure out again what this breaking point here is, because we're going to get a different formula from 0 to b, and then from b to pi over 2. Right? So area 1, this area here, we're going to integrate from 0 to b. Let me draw it in red. All right, so along this interval, we integrate the areas of these rectangles. The height of the rectangle is going to be the top cosine of x minus sine of x. Cosine of x minus sine of x. This is the height of the rectangle. You multiply by the very tiny base, right? And you get this infinitesimal area. Integrate, you get the whole thing. And area 2 will be plus integral from b 2 pi over 2. And now the height of these rectangles is going to be the value on the top, which is sine of x, minus the value on the bottom, which is cosine. Minus cosine. Right, so as long as we figure out what b is, then we're good to go and compute this area. So figuring out what b is a similar process. Well, what is b? It's the x-coordinate of this point here, which is in the intersection of these two curves, right? So one way, let me see, maybe I'll write over here. One way of seeing this is, okay, b is the x-coordinate. What is the y-coordinate of this point? Well, this point is in this purple curve, which is the curve given by this equation, y is equal to sine of x. So all of the points in the purple curve need to satisfy this equation. The y-coordinate has to be sine of the x-coordinate, so it has to be true for this red point as well. So the y-coordinate is sine of the x-coordinate, which is b. Sine of b. Right? This is because this red point is in the purple curve. But this red point is also in this blue curve, given by y equals cosine of x. Right? So, okay, b is the x-coordinate, and the y-coordinate, because it's on the blue curve, is equal to cosine of b as well. Right? But these are two ways of writing exactly the same point, which means that these y-coordinates, they are the same, right? It's the y-coordinate of this point. So b, we see, has to satisfy this equation that sine of b is equal to cosine of b, which you can solve by using the unit circle again. So if we draw here the unit circle, doesn't have to be super precise, but in the unit circle, if you choose any point with a given angle, oh, that wasn't a good choice. If you choose any point here with a certain angle, theta, the coordinates of this point are given by cosine theta, sine theta. Okay? And then you want to know, well, if you want to solve sine of b is equal to cosine of b, you might look for what is the angle b where the x and y coordinates are going to be the same. Right? That's one way that you can solve this equation. So you can just look at the line y equals x, all the points with y coordinate equals to the x coordinate. This is the diagonal line, right, in the xy plane. And these 2 points are going to be the solutions of this equation. This point here has angle, it's right in the middle here, right? So the whole thing is pi over 2. This thing here is pi over 4. And this angle here, you can see is pi over 4 plus half a turn. So pi over 4 plus pi, which is 5 pi over 4. But so the solution of this equation here is b is equal to, well, okay, so you can take pi over 4, and you could also multiply any multiple of a whole lap, right? Because then you will solve as well. Or 5 pi over 4, and you could also multiply any multiple of a whole turn. But we are trying to find a solution of this between 0 and pi over 2, right? So for angles between 0 and pi over 2, the only solution is this, is pi over 4, right? So you can cross out the other stuff that we figure out here. So this is not the solution we want. Pi over 4 plus 2 pi would leave the interval 0 to pi over 2, so we can ignore this as well. We find out that b must be pi over 4. Okay. And now that we found b, we can compute the area. So the area of the region we want is the integral from 0 to pi over 4. Now that's b. And I think in the beginning cosine is on top, right? Cosine x minus sine x dx plus the integral from b, so from pi over 4 to pi over 2 of sine of x minus cosine of x. All right, so here we can just use the fundamental theorem of calculus. An antiderivative of this function, antiderivative of cosine is sine. An antiderivative of negative sine is cosine, plus cosine. Right? Cosine, if you take a derivative, you get negative sine. Right? So plus cosine. If you take a derivative of this, you get cosine minus sine, which is exactly what you need. This you need to evaluate at pi over 4 and 0. Plus, okay, antiderivative of this function, antiderivative of sine is negative cosine, right? Derivative of cosine is negative sine, so derivative of negative cosine is negative sine, which is positive sine. And an antiderivative of negative cosine is negative sine. Okay. Evaluate at pi over 2 and at pi over 4. Okay, so now it's just plugging it in. So here you're going to get, plugging in pi over 4, you get sine of pi over 4 plus cosine of pi over 4. That's the top term minus the bottom term, sine of 0 plus cosine of 0. Okay, plus top term with pi over 2, negative cosine pi over 2, negative sine pi over 2, minus the bottom term, so negative cosine pi over 4 minus sine pi over 4. Almost running out of space here. Okay, so evaluating all these things, you can evaluate all of them with the unit circle, but I'll just write down what they are. So this is a root 2 over 2 plus root 2 over 2 minus 0, sine of 0 is 0, minus 1, cosine of 0 is 1, minus cosine of pi over, excuse me, cosine of pi over 2 is 0. Okay, so this you can always figure out using the unit circle. Pi over 2 is right here. Cosine is the x-coordinate, which is 0. Okay? So this is 0. Minus sine of pi over 2. Sine of pi over 2 is 1, so that's minus 1. And this is plus root 2 over 2 plus root 2 over 2. Yeah. because there's two negative signs here, right? So it turns into a plus. And so these two together gives you 1 root 2. So there's this and there's this one. So you get a 2 root 2. These two negative ones together will turn into a negative 2, which is equal to 2 times root 2 minus 1. That's the area. 2 root 2 minus 1. All right. So I'm going to stop this video here. This is exactly what we covered in the Zoom meeting. And then in the next video, I'll cover the last part of section 6.1 of Stewart, where we're going to talk about curves that are given in terms of y instead of x. Right? See you soon.